We can start. So, we submitted the paper to the Empirical Software Engineering Journal. It was April 2012. And we received the first evaluation on September 2012. Remember that we did actually an experimentation on artificial blob to tune the parametering of our approach. Then we also performed, based on the state of the art, an evaluation based on quality metrics. This is the comments by reviewer number 1. You will see very often reviewer number 1 in the slides. The problem with this paper, as with all other papers that I read, lies in the improper validation. And the problem is that actually we use just 2 quality metrics to evaluate the quality of the design, that is cohesion and coupling. So the reviewer complained about the fact that we are just measuring 2 design goals, that is cohesion and coupling. In order to evaluate the quality of the design, you should consider other factors that are not only cohesion and coupling. So, I will totally reject the result of the first experiment. But as you probably know, there are also other reviewers. And we got comments by 3 reviewers. And reviewer number 2 say, "Oh, I really like section 4. Can you guess what is inside section 4? The evaluation based, of course, on quality metrics. So this is the reason why we did not remove from the paper the evaluation based on quality metrics, but we need to find another experimentation of the type of evaluation. Specifically,
what was the comment by the associate editor then?
The comment
in this case, the associate editor is supposed to do his job.
The associate editor actually suggested us to not remove the evaluation based on quality metrics because it provides some insight, but we need to evaluate better our approach. And specifically on the evaluation based on quality metrics, we can conclude that, of course, refactoring techniques should not increase coupling and or reduce cohesion. Quality metrics can help you in performing a first assessment of the approach, so it's a kind of sanity check. But a quality metrics based evaluation cannot be the core of your evaluation. You need to evaluate the benefits of your approach. You need to evaluate the usefulness of your approach. And you cannot measure the usefulness of your approach based on metrics. So we need still a problem. We need an evaluation design for our approach. And in order to evaluate the usefulness of an approach, you need to involve developers. You need, as I said in the introduction, you need to put your approach on the field, allow people to use your approach, and collect data. So our idea is, the experimental idea once again, is the proposed approach able to suggest meaningful refactoring operations? So instead of measuring cohesion and coupling, instead of measuring the quality improvement, we want to analyze the meaningful of the refactoring operation. Are the refactoring operations meaningful? The idea is the following. Take a block, refactor it using the proposed approach, and ask developers whether or not the refactoring operation is meaningful. So something that you suggested in the first part of the talk. So instead of measuring with the quality metrics the improvement, we want to involve people that evaluate our approach. So in the first experiment, we just used students and we just used people to identify a set of real blobs. Here we want to involve people in order to evaluate the meaningful of the proposed approach. What do we need here? A quite large number of blobs, of course, and a good number of practitioners. This second part is quite difficult because involving practitioners is difficult. And it's difficult because for practitioner, time is money. So you have 2 options. If you want to run the experiment, probably you have to pay practitioners. And if you are a PhD student in Italy, forget it. Because you don't have money to pay your travel, so probably you don't have money to pay practitioners. The other option is to find a way to overcome this obstacle. And the dilemma is that we need to understand how practitioner refactor a blob, but without involving a practitioner directly. How we can do? Well, we can mine the evolution history of a software project in order to analyze how people, how developers have refactored blobs. In other words, our experimental idea is the following. The refactoring operations suggested by the proposed approach, that is the code construct, are meaningful for software developers, the effect construct. So this is the experimental idea. Code construct, the relationship between code construct and effect construct. The scoping is very similar. The objective of the study is once again our technique. The purpose is to evaluate the benefits of the proposed approach, once again. But this time the benefits is not in terms of quality improvement, but in terms of meaningful of the proposed refactoring operation. Once again, the perspective is both from researchers and practitioners, and the context, this time, is represented by, once again, a set of manually refactored blobs, not manually identified blobs. It's a set of manually refactored blobs. So this means that we want to derive from the history of a software system a set of classes that have been refactored. Okay? A set of blobs that have been refactored. How we can do this? Well, there is a tool called a Ref Finder that is able to identify between two releases of a software system the refactoring operations performed on the system. This means that comparing two subsequent releases of a software system, we can identify all the refactoring operations performed on the system. So this means that starting from a particular revision, okay, starting from a particular release of a software system, I can identify two classes that are two or three classes that are the results of an extract class refactoring operation. This means that in the previous release of the software system, these two classes were in a blob. So I can derive from the refactoring operation the original blob. Now I have the blob and how the blob has been refactored. This means that on this blob I can apply my approach and compare the refactored class by my approach with the original classes. So once obtained the classes, I can compare. And once again, I can use the merge FM. So similar to the design of the first experiment conducted on artificial blob, I can do here the same. But instead of having artificial blob, here I have real blobs. And how the real blobs has been refactored by the original developers. Which are the traits to validity of our approach, of our experiment? The experiment is the reliability of the oracle, because we derived the refactoring operation from the history of the software system, but we need to be sure that the refactoring operations were correct. And in order to guarantee this, we observe whether or not the refactored classes have been changed in the subsequent release. So in other words, if there are some drawback operations performed by the developers, if the developers change the original refactoring operation. So we selected only the refactoring operations that were actually considered correct. And of course the number of refactoring operations. Because RefFinder is a nice tool with a good accuracy, but is not able to identify extra class refactoring operations. But if you think the extra class operation, when you split classes, actually you perform several refactoring operations, this move class or extract method. So extract class refactoring can be viewed as a set of atomic refactoring operation. So RefFinder is able to identify the atomic refactoring operation, and we need to manually identify this refactoring operation and say, okay, this group of refactoring operation is actually an extract class refactoring operation. And the number of refactoring operation, the extra class refactoring operation, is quite low because we want to be sure that the group of atomic refactoring operations that we identified are really extra class refactoring operations. This is the analysis of the result. As you can see, our approach is able to refactor classes with an accuracy higher than 91%. This means that the refactored classes are similar to the original classes, are very, very similar to the original classes. In other words, our approach is a good starting point for obtaining the original class. I'm saying this is a good starting point because in order to be completely automatic, you should obtain here 100%. So you are able to reconstruct the original classes. But with a similarity of 91%, the developer can run the tool, obtain a first splitting of the classes, and then can adjust and move some method to a class from another, and so on. Good. We have now a stronger paper because we have three different evaluations. The first one that actually is not really an evaluation, is just conducted to perform a parameter tuning. The second one that is based on the quality metrics that was particularly liked by reviewer number 2 and was not liked by reviewer number 1, but still is an evaluation. And then we have this third evaluation that is based on historical information. We submitted the paper on December 1st. The paper is now 38 pages, so 6 pages more. And we obtained a second evaluation of our paper on February 2013. And this is the comment of reviewer number 1. Evaluation based on historical information looks like a good idea. Wow! We made reviewer number 1 happy. No. However, we cannot know the reasons behind the refactoring operation performed by developers, nor if they are being performed manually or by using automatic tools. So, which is the reason why people refactored the logs? And the reviewer number 1 asked these things involve developers in evaluation of the approach is needed. We have the same problem. The problem how to involve practitioners. Once again, practitioners are difficult to involve. But we have computer science students. So we have students, and students can be involved for free, more or less. So we can conduct the experiment with students. There are different opinions on involving students in empirical studies. Actually, when you perform an experiment and involve students, this is one of the main reasons why your paper will be rejected. Because people can easily say, oh, you are performing the experiment with students. Students, by definition, are stupid. So they are similar to monkeys, or something like that. Probably these people forget that students are humans, first of all, and especially master students are very, very similar in terms of experience with junior developers. Because at some point, students stop to be students and probably start to be developers. So there are some studies that actually analyze the difference between practitioners and students, and they claim that students are not far from junior software developers, as I say. And it's not always easy to identify differences between them. So performing an experiment with students should be still reliable, so should be still good. even if you find a reviewer that is not so convinced about that, this is one of the main reasons that he or she can use in order to reject your paper. This is a price that you have to pay. You avoid to involve practitioners, involve students, but remember that there could be a reviewer that rejected the paper just for this reason. We involve students, of course, and our experimental idea is the following. The refactoring operation suggested by the proposed approach, cause-construct, provides a better division of responsibility among classes. So this time we use a design very similar to the one suggested by your colleague in the first part. That is, this time students analyze the refactoring operation proposed by our approach and say, oh, this operation, this splitting, provide a better division of responsibility. Okay? So this is the experiment scoping. As you can see, the context now is different. There is a set of manually refactored blocks and the computer science master students. The context here is different because for the first time we see that the context is represented by objects and subjects, where subjects are participants, are students. How we select subjects? Well, when you perform an experiment with subjects, the first step is select subjects, select participants. You have a different strategy. Some of them are based on probability sampling. Simple random sampling, you have a population of students and you just pick some of them, or systematic sampling where you divide students in groups and pick one for each group, or non-probability sampling, that is convenience sampling and quota sampling. This one is one of the most used convenience sampling because you take the nearest and the most convenient people. And this is what we did with students. We send an email. Guys, there is the possibility to participate in an experiment. The goal of the experiment, the design of the experiment is this one. You have to evaluate the refactoring operation made on the blog. Do you want to participate? Yes or no? And of course, we take as subject all the students that answer yes to our request. And what about the size of the population, the number of subjects that you involve? Of course, this is an important parameter. That depends, of course, on the variability of your population, because the higher the variability, the higher should be the number of the selected subjects. And also, the population size, the size of your subjects, influence the statistical analysis that you can perform on the data. If you have few observation points, if you have few subjects involved in the experimentation, it's difficult probably to apply a statistical test. Okay? If you have a huge number of subjects, you can apply, of course, tests. So the analysis of the data influences the choice of the sample size. In our case, we selected as objects the 17 blobs that we identified mining the history of open source software systems. So the ones that the refactoring operation that we identified with the RefFinder and that we manually validated as extra class refactoring operation. For the subjects, we involved 50 students, look convenience sampling, of course, in order to give some background to students to refactoring before the experiment. Students attended a seminar, 2-hour seminar, in order to give them information on refactoring and refactoring operations in general, just to introduce the context of the study. Even if all the students had in their bachelor curriculum at least one exam on object-oriented programming in Java and on software engineering. So the background is good. Which is the design? The design is very simple. There is just a point that could be that should be highlighted. We show a student a blob, so the original blob, and show to a student how the blob has been refactored by our approach. And we ask to the student a simple question. The proposed refactoring result in a better division of responsibility, and students had to answer to this question using a Likert scale from 1 to 5. 1 means absolutely no, and 5 means absolutely yes. Okay? But more important, in the survey that we performed and we provided to the students, we also, time to time, show to students a blob and a random splitting. So we split the blob not using our approach, but using a random approach. This is a kind of sanity check, because when you involve students, very often students participate to the experiment just because it's the professor that asks the students to participate to the experiment. Okay? In order to be sure that they are taking the experiment with the correct spirit, this is a kind of sanity check, because if we have a student that actually answered absolutely yes to the better division of responsibility of a random splitting, well, this is a student that should be removed from the population, physically probably. The variables of our experiment are refactored and level of agreement. Refactored is the independent variable and is divided into treatment that are our approach or random, so we can control the splitting of the blocks, our approach and random, and with the dependent variable is the level of agreement. So the higher the level of agreement, the higher is the division of responsibility, the better division of responsibility of our approach. Which are the traits to validity of our experiment? Of course, we have here an important traits to validity that is represented by the student involved as subjects. And here we have to discuss in your paper which are the limitations of your study, saying which is the background of the students in order to give information on the reader on which is the context, more information on the reader on which is the context of your study. These are the results. As you can see, students perform their task seriously, and as you can see here on the two systems, the results of the performances of our approach are really good. Specifically, we obtained an average score, an average level of agreement equal to 4.3. That is good. The scale is 1 to 5. Wow! We have now a much stronger paper. We submitted it on March. The page of the papers now are 44. And we received the evaluation on April 8th. Almost done. No. These are the comments of reviewer number 1. The question asked to the students, are the responsibility better separated, is not sufficient. And I have to admit that the reviewer is right again. This is not the right question to ask, in my opinion. The right question are, would you split the class differently? How? Why? And would you have split the class at all? Why? In other words, what is asking the reviewer is to collect qualitative data, is to collect the reason behind a score. And he or she is right. We just collect numbers, but we do not collect opinion. Actually, we are considering our subjects not humans. We are just asking them to select a value on a Likert scale from 1 to 5. But we are not asking them why you are answering in that way. Very often we hate our reviewers because they reject our paper, of course. But I think that in my experience, this is one of the best experiences that I had with the reviewer. I can say now that this reviewer actually played an important role in the writing and in the research that we conducted. So he or she was really able to provide us very, very important comments, and actually it contributes to our improvement of using empirical methods in software engineering. So I have to thank this reviewer for his job. Probably he or she should be one of the co-authors of this paper, because actually he worked a lot with us, asking improvement and so on. Well, based on this comment, we have another problem. How to collect qualitative data? Once again, we have students. We do an experiment with students. And look at the importance of the error that we made. We involved 50 students, but we did not ask them the right question, and we involved 50 students. So we do the experiment with 15 master students. This time the sampling is lower. The object of this study this time are 11 blogs refactored by original developers, and what we asked? Exactly what the reviewer said. Okay? So this is a reviewer-based template survey. Would you split this class? Yes. Why? Would you split the class differently from that to provide a refactoring solution? Blah, 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 blah. These are the results, and these are the comments that we collected. As you can see, we used the comments left by students in order to provide rationale behind their score. And the students say that the refactoring operations were useful because there is good comprehension, I like the main responsibility implemented in a class, the extracted classes are cohesive, and so on. And this is a comment of one of the people, one of the students involved. Without the refactoring suggestion, it would be too difficult to identify the main responsibility of the classes. So, this comment further support the need to refactoring blobs. Now we have a super strong paper. So we submitted the paper. The number of pages are 47. And on May, we received the fourth evaluation. This time, we obtained the comments just by the editor that said, okay, you did an amazing job, thank you, I recommend acceptance of this paper. So, mission completed. We were able to convince the reviewer that our approach is good. We perform an empirical study in an artificial scenario in order to just tune the parameter. We perform a metrics-based evaluation just to provide a sanity check that our approach was correctly implemented. And then we perform experimentation with subjects in order to evaluate the usefulness of our tool. Gabriele is a paper machine, of course, and he moved to move class refactoring, another refactoring operation. Here the design problem is one of the main reasons for architectural erosion is inconsistent placement of source code classes in software packages. That is something highlighted by Max this morning. Very often you put the class not in the correct package because of time pressure. So at some time you have to review the remodularization of your system in order to increase coupling and increase cohesion and decrease coupling. There are a lot of papers that take in input the system and redo the modularization of the system, providing you a new design, a new organization of the classes in different packages. One of the main, this is called Big Bang remodularization. As said by Max, you can apply genetic algorithm that find the best clustering of the classes of your system. But the Big Bang remodularization has an important drawback. You completely change the design of your architecture. So I have a system here that is a kind of architecture. It's not good, but I know how the classes are organized. I give this system to a tool that completely changes the organization of my classes in package. This is not anymore my system. I need to read and to analyze all the classes in order to understand how the approach places my classes. This is the reason why, with Malcolm and Dennis, we derive a new approach for the remodularization of software system that we call it R3, rational refactoring via RTM. RTM is a topic analysis technique. R3 is an approach able to remodularize a system by making a single move class operation. So instead of changing all the organization of the system, this is an incremental approach. I suggest you just one move class operation. Move this class from here to here. Move this class from here to here. So a fine-grained approach instead of coarse-grained approach. In addition, R3 is the first refactoring method that provides you also an explanation on why you should move a class from one package to another. Okay? Specifically, this is a refactoring operation suggested by R3. First of all, R3 gives you a confidence level, that is the confidence of the tool in suggesting the refactoring operation. The higher is the confidence, the higher is the accuracy probably of the refactoring operation. So the tool here is pretty sure that you should move this class from one package to another. In addition, the tool gives me this indication: move this class that implementing the topics, profile, model, and URL from its actual package that groups the topics tree, node, explorer to the package profile, grouping the topics profile, OCR model. So in this way, you can have an idea on why the tool is suggesting to move a class from one package to another. RTM is used to extract these topics, so it's used to extract the responsibility of a package, responsibility of a class, and also to identify the most appropriate package for a specific class. How to evaluate this tool? Well, it's easy. We have experience now thanks to the MC reviewer. We know how to do this. We can perform the experimentation on metrics, that is a sanity check. We can perform the experimentation with developers in order to analyze the benefits, the usefulness of the tool. So our experiment idea is the following. Refactoring a system with R3, that is the code construction, we are able to improve the quality of a software system, that is the effect construct. Based on this idea, we can perform two kinds of experiment. One that is metrics based, where we measure the quality in terms of cohesion and coupling, and the other experiment, analysis of meaningful of the refactoring operation, the quality here is measured in terms of meaningfulness of the operation suggested by R3.